So, there is a way for us to find a 2 by 2 matrix without using Gauss-Jordan elimination. How do we do that? Now, let's say we have a given matrix A, whose elements are A, B, C, D. Now, to find the inverse of A, we are given with this formula. 1 over AD minus BC multiplied to the matrix D negative B negative CA. So, what happens is that we kind of multiplied this minus then the product of this. That is actually that denominator. Then we interchange E and D. We did not interchange B and C, but we made them negative. So this is one formula, and this works only for a 2 by 2 matrix. Let's have some examples. We're given with two matrices here that are 2 by 2. Pause the video and try to see if you can find the inverse of the matrix using this formula. Alright, so let's start with letter A, which is a matrix A with the entries negative 3, negative 1, negative 2, and 2. So following our formula here, we'll have the inverse of A will be equal to 1 over 3 times 2 minus negative 1 times negative 2. Oops, wait a moment. There you go. Let's fix that. There. Multiplied 2. This is 2. This is negative of negative 1. This is negative of negative 2. And 3. So there. So finalizing this one, we're going to have here, this is actually 1/4 multiplied to the matrix 2, 1, 2, and 3. So finally, we're going to have the matrix 1/2. There you go. This is 1/2, 1/2, then 1/4, 1/2, then 3/4. So therefore, A inverse is equal to 1/2, 1/4, 1/2, 3/4. And if you would like to try if this is the real inverse, you can multiply this to A and get I sub 2. So let's now do letter B. Let's pull that up. There you go. For letter B, we have matrix B, which is 3, negative 1, negative 6, and 2. So B inverse would be, first that denominator, 3 times 2, minus negative 6 times negative 1. Then, we multiply that to the matrix. This becomes 2, because we interchange that. Then negative of negative 1. Then this becomes negative of negative 6. Then this becomes 3. However, here, as you can see, this actually becomes 1 over 0. But this is undefined. So therefore, all we can conclude is that B has no inverse. And you can try by Gauss-Jordan to see if this is actually true. Now, there are some properties of our inverse matrices. So if A is an invertible matrix, K is a positive integer, and C is a non-zero scalar, then A inverse, A raised to K, C, A, and A transpose are invertible, and the following are true. First, when we get the inverse of A, it just goes back to A. Next, the inverse of A raised to K would just be actually the same as getting the inverse of A first, then multiplying it to itself k times, or raising it to the kth power. If we want to get the inverse of the product of a scalar and a matrix, it's the same as getting the multiplicative inverse of the scalar and multiplying it to the inverse of A only. Lastly, getting the inverse of the transpose of A is the same as getting the transpose of the inverse of A. These properties are some of the things that we can use whenever we're going to work with the different inverses of matrices. And those are some more informations regarding inverse matrices.